This video is going to be about the three types of eigenvectors in factor analysis. It is helpful in understanding factor analysis to identify the three types of eigenvectors that play a part in the factor analysis formulas. The first is the K matrix, or it's actually vector K1 and vector K2 joined to create a K matrix. And where we get this K matrix is if you go to the last video, video 4.8, where we did a demonstration of a complete factor analysis, we can find those K vectors. And as you remember, these vectors are normalized to 1. So I have the last video's data up here, and we got a K1. If we look at step 3, we created a K1, which was a true eigenvector, and we also got a true eigenvector that we called K2. So what I'm going to do, I'm just going to copy, go back over and paste this here to create my K matrix. I could just enter the data in, but I want to show you where I'm getting it from. Okay. Now, when matrix K, when pre-multiplied by its transpose, will have an identity matrix as its product, as you can see in this formula here. So I'm going to copy this K matrix and do a paste special and click transpose. Then I'm going to do matrix multiplication to multiply these two together to show you that it does indeed equal the identity matrix. Since they are normalized to 1, the diagonal entries will be equal to 1, and the off-diagonal entries are equal to 0 because the eigenvectors are orthogonal to one another. And what we mean by saying that two eigenvectors are orthogonal, we're saying they're independent of one another. So the second form of the eigenvectors that we have encountered, F, is the factor loadings matrix, which consists of the eigenvectors normalized to their eigenvalues. When a similar product matrix is created by pre-multiplying F, as shown in this equation, by its transpose, the resultant matrix is a diagonal matrix of eigenvalues, which we denote by this lambda here. And we can go back to our Excel spreadsheet that we found the factor loadings. I'm just going to copy these and paste them into here to get our F matrix. And we can copy and do a transpose, paste. So when we multiply these together, we do indeed get zeros on the off diagonals, and on the diagonals we get eigenvalues. If we go back to the last video, we notice from our factor analysis summary table that the eigenvalues are 1.97 and 0.887, which is what we get here. So that is the factor loading matrix pre-multiplied by its transpose to get a matrix of the eigenvalues. Now, the third form of the eigenvectors used in factor analysis is this transformation matrix T. The matrix T consists of eigenvectors normalized to the reciprocals of their eigenvalues. When the product matrix is created by pre-multiplying T by its transpose, as shown in this equation, the resultant matrix is a diagonal matrix of reciprocals of eigenvalues. So essentially this will just be equal to 1 over 1.972 and 1 over 0.887. And I'm just going to do that out here so we can show you. Let's have this equal to 1 over 1.972, and we get 0.507, and this one be equal to 1 over 0.887. And we get 1.127. Now, this T matrix, in fact, has the following values. It has 0.260, 0.964, then we have 0.452, negative 0.429, and on the last row, 0.485 and negative 0.117. So we can take the transpose of that and put it here as well. So let's do matrix multiplication and see if we come out with these values I have to the right for the reciprocal of the eigenvalues. And in fact we do. Now the transformation matrix T, you're probably wondering how we created it. It can be created by post-multiplying the matrix of factor loadings F by the matrix, the inverse of lambda, which we have here. A diagonal matrix of reciprocals of the eigenvalues. So, so we can take F, let's copy and paste that down here. And this is the formula we're going to use, T equals F times inverse lambda. And what I'm going to do is just copy that in here. Sorry, let's try that again. So this is going to be equal 1 over our eigenvalue equal 1 over the other eigenvalue. And these have zeros. So when we multiply these two matrices together, we should get our T. And that's how we got it. So we already knew the inverse of lambda. We just take the reciprocal of the eigenvalues. And we already knew the factor loading. So that's how we calculated T here. So those are the three types of eigenvectors that play a part in the factor analysis formulas that we're going to talk about this time. Enjoy the rest of your day.